All right, I'll get started here. Let me we begin with a word of prayer. So, Heavenly Father, we thank you again for this day, for this time we have to meet together, study your creation. Just pray again that you'd guide our steps and just encourage the students if they're struggling, just to get help where they need to, and just ask good questions, Lord. In your name I pray, Lord Jesus. Amen. So Dr. Sperano has kindly left us a solution to a trig substitution over there, which you're welcome to take a gander at. Well, while I'm putting this thing away, do you guys have any questions about anything in particular?
What was you said we go over tomorrow?
Oh, the quiz? You want to know what the answer is? Yeah. Yeah, there's lots of questions. What's that?
No, it's just question 2.
Question 2?
On the quiz, yeah. If you could go over it, that would be very helpful.
Yeah, actually I'm going to have to do that tomorrow because I left my solution upstairs and I don't want to just burn class time on it. But essentially it's just the same way we did the integral of sine. We did the sine 4 theta thing. So we split, oh, fine, I can, just a second. Let's get it over with. So it's just this. Well, fine. Well, oh well. It was a nice problem. So long. Hey, that's kind of like the one we had, right? Was on the board here is not unlike question 1 on your quiz, was it? Let's see here. So anyway, sine 3 theta, you can just write as sine of theta plus 2 theta, which then is sine theta cosine of twice theta plus cosine of theta sine of twice theta, right? And then you can break these up, yeah? So like sine theta is sine theta. What's cosine of 2 theta? 1 minus 2 sine squared theta. There's a few different ways to go there, but that's one of them. And then you've got plus cosine theta. Sine 2 theta is 2 sine theta cosine theta. But you were given that x is equal to the square root of 3 cosine theta. Isn't that right? Have I remembered that right?
Yes.
And so that suggests a triangle with a theta here. The adjacent side is x. The hypotenuse is square root of 3. The other side would be the square root of 3 minus x squared. So then that tells you that, like, among other things. So we already know cosine theta is like, x over root 3. And sine theta, what's it? Sine theta would be the square root of 3 minus x squared over root 3. And you just plug those in, and that's it.
Thank you.
It does simplify down a bit, but I didn't. If you simplified it nicely, I gave you like 5 points bonus. Yep.
If you just multiply that by 3 to be sine 3 theta, is that like an incorrect thing to do?
Just multiply it by 3.
Yeah, because it's like sine 3 theta, so like that was equal to sine theta.
Yeah, that's not true.
It's not true.
No, sine is not linear.
Yes, sir.
We can't just pull 3's into sine. It's not like that.
Yes, sir.
I wish it was. I mean, that would make things it would make life way easier. But unfortunately, sine of 3 theta is a quite different function than sine of theta. Its period is 2 pi over 3, whereas sine theta has a period of 2 pi. So they're not nicely related as like a scalar multiple of one another. More complicated than that. Sine 3 theta wiggles 3 times every time sine wiggles once, So in terms of density of wiggles, sine 3 theta is a different animal. Let me put this away. So I should have the solution to the quiz posted here, guys, and, before close of business today. I do have the solution. I just left it in the folder in my office. And, so, any questions about the homework? All right, so let us talk then about improper integration. What's improper integration? Do you guys know? Integration to infinity? Yeah, so it either explicitly involves infinite bounds, right, plus or minus, or what else? What's the other case? Or implicitly, has some divergence for the integrand. All right. Or both. Or both. It could have both. All right. So this is, oh, thanks, you guys got it. This is what is involved in improper integration is dealing with such cases, right? And I could spend the next 20 minutes writing a formal definition for you, right? for how we define improper integrals in all the various different cases. But I think what's a better approach, and you can look at that definition. It's in my notes. It's in gory box-like detail there, yeah? But I think the best approach for us is to just proceed by examples, all right? And the other good aspect to this is one of the things I have not yet emphasized at all with integration, just a little bit earlier, is integrals with bounds, yeah? We've been doing indefinite integration for like over a week now, right? I don't think I've put bounds on an integral for some time, have I? Some of the homework, yeah. But certainly not in here. So let's get, we're going to do that. We can't avoid it now, because these are all basically under the family of definite integrals. I would say that these fall under the family of they're basically sort of modified definite integrals. And what's the answer to a definite integral? Right. So that means that the answer is what? Either a number or an admission, the integral that's integral does not exist, right? And to say it does not exist, sometimes we could be more precise than that, right? Sometimes does not exist means that the integral grows without bound, in which case we write infinity. Sometimes it doesn't exist, but it grows without bound in the negative direction, and then we write minus infinity. So technically, a subcase of does not exist are sometimes plus or minus infinity. These are special cases, right, of non-existence. Okay, that's the big picture. Let's work some examples, all right? So let's start with something relatively simple. Example 1. What would we mean integral from 0 to infinity of, let's say, e to the minus x dx? What does this mean? So what this means, by definition, that I haven't written, is that the limit as t goes to infinity of the integral from 0 to t of e to the minus x dx, that's it. This is the definition of this integral. Okay? That's it. So what is the integral of e to the minus x? So we get what? We get minus e to the minus x, right? Fundamental theorem of calculus part 2. We evaluate, from 0 to t like so. What does that give us? Limit as t goes to infinity of minus e to the minus t minus a minus 0, right? So plus e to the 0. So what's the answer here? So what happens to e to the minus t? Do you guys know? Yeah, so you need to, if you don't know about that, you need to take ownership of it, right? So the graph of e to the t, e to the minus t looks like this, yeah? So what happens as t goes to infinity? This piece goes to 0. That's just a basic limit, right? And so what are you left with? E to the 0, which is? 1. Now what does this number 1 mean? I mean, that you say, well, that's the answer, but what does it mean geometrically? Do you guys know? Yep.
Basically, all the area under the curve from 0 to infinity.
All the area under the curve from 0 to infinity, right? So it's saying that this strip right here, right, that goes on and on without end, has finite area. And the area of that shaded region is 1, despite the fact that one of its legs has length infinity. Well, 2 of them, right? And yet the area which is bounded is finite in this precise sense. Okay? So there's your first example. Let's look at another example. All right, so what if we had, say, the integral from minus infinity to infinity of dx over 1 plus x squared? This is a nice example. All right. So here I have to, now this, to see why I have to make this more complicated than you might think at first, you'll have to wait till the next example, all right? But the way we do this is we pick some number in the middle. It doesn't matter what you want. Let's split it at 0, right? Because 0 is nice. So minus infinity to 0, dx over 1 plus x squared, yeah? Plus the integral from 0 to infinity of dx over 1 plus x squared, okay? So that's how we're going to split it. And then how do I define those? Yeah? Oh, you're okay. You can't. I know it's a bit much sometimes to like take notes and to do the camera. I get it. I used to rotate students through and like have a designated camera person every time. I probably should get back to that. But anyway, so, but then that makes you guys move seats. You guys like to stay in your seat, you know? I don't know. So, by definition, right, this is the limit. Let's say as s goes to minus infinity of the integral from s to 0 of dx over 1 plus x squared plus the limit as t goes to infinity of the integral from 0 to t of dx over 1 plus x squared. What's the integral? If you don't mind, I'm going to kind of skip the FTC part 2 and go straight to what we get. So what we get is limit as s goes to minus infinity of inverse tangent of 0 minus inverse tangent of s, yeah, plus the limit as t goes to infinity of inverse tangent of t minus inverse tangent of 0. By the way, you can start to see at this point that if I had, instead of using 0, if I had used any other number, it wouldn't have turned out different, would it? Like, think about this. If I had instead of putting 0, right? Suppose I had put like a C here, and I'd put a C here. What would have happened? It would have just put a C here, and it would have put a C here. What would have happened then? They would just end up canceling, right? Assuming that the limit exists, why does it exist? What are the limits? And what is this limit? What's the graph of inverse tangent look like? Do you know? Because you should. Maybe you don't. Here's the graph of tangent. It's got vertical asymptotes at plus or minus pi over 2, right? So what's the graph of inverse tangent look like? The vertical asymptotes become horizontal asymptotes, right? And so the graph of inverse tangent, same shape basically, but just run sideways. So it looks like, yeah, come on, get out of there. There we go. Whee! Like that. So there you go. That's the graph. Y equals inverse tangent of t. right? So it's got horizontal asymptotes of plus or minus pi over 2, right? This is an important limit. You need to know this. It comes up in a lot of examples. Okay? So if you don't know it yet, then please learn it. So what's the limit of inverse tangent of s as s goes to minus infinity there? Negative pi over 2, right? So we have minus a minus pi over 2, right? And then what? Right? Yeah, and then plus pi over 2. And the other terms cancel, all right? And so what's the answer? Apparently, pi. The answer is pi. Graphically, what's going on here? What does this mean? What does the graph of 1 over 1 plus x squared look like anyway? Do you guys know? What does the graph of y equals 1 over 1 plus x squared look like? Have you ever graphed it? You know what it looks like? Could you figure it out without a graphing calculator? It's like a bell curve, right? If you differentiate that, you get what? You get minus 2x over 1 plus x squared quantity squared. You can easily see the only critical number of that's 0. Therefore, it has a min or max of 0. A moment's reflection will realize, we'll quickly show you it's a max, right? And then you can find inflection points if you want to make it all pretty and stuff. But basically, like you said, it's a bell. So it looks like this. And what's the limit? What's the limit as x goes to plus or minus infinity? Well, it's 0, right? But we just calculated that the area under this bell is what? Yeah, this area is pi. Which is kind of neat, right? And the initial splitting just corresponds to doing what? Like basically I said, let me use some color coding here. So maybe the green area is like this one, yeah? And then the other one, let me use another color here. So the other one, if I have another one, this hideous Carolina blue. This other side would be that area. Oh, sorry, I really need to get some more markers. I find myself using the Carolina blue. It's distasteful. But anyway, so if you split it at 0, you can see that there's pi over 2 area to the left and pi over 2 area to the right, right? By the symmetry of the problem. This is an even function, is it not? What's an even function? Do you guys know? Symmetrical across the y-axis, right? So that means that f of minus x is equal to f of x, right? What's it mean for it to be odd? Right. So do you guys know the theorem about integrals of even and odd functions? No? All right. Maybe? Here's the deal. Integral from minus c to c of f of x dx is equal to 0 for f of x odd, right? And the integral from minus c to c of f of x dx is equal to 2 times the integral from 0 to c f of x dx if f is what? For f even, yeah. These are very useful things to know at times, yeah? And they're completely legitimate to use kind of, unflinchingly, as long as your bounds are finite. But you got to be careful when your bounds are infinite. There are some issues, all right? Let me show you what I'm talking about. Let's calculate. And I'm going to show you a danger here, a common misconception. Common misconception here. Let's try try to calculate the integral. Oh, I don't know. X dx from minus infinity to infinity. All right? And let's calculate this as the limit as t goes to infinity, all right, of the integral from minus t to t. Yeah? Of x dx. I mean, you might wonder, why didn't we do that last time, right? Why did I have to do two improper integrations? Why wouldn't just one do? Can't I just go to infinity like this? Right? Okay. So what happens here? This is an odd function. F of x is odd. This integral is 0. The answer is 0. Unfortunately, that's not right. Because this is not how the integral from minus infinity to infinity is defined. And it matters because it's not defined this way, you get a different answer this way versus the correct way. The correct way is that you have to deal with it separately. In other words, the infinity and the minus infinity, they are not connected. All right, so this is technically defined. I mean, you can do 0. We can do minus infinity to 0 of x dx plus the integral from 0 to infinity of x dx. And so what you're getting is like the limit as, let's say, s goes to minus infinity of, you know, x squared over 2 evaluated from what? From s to 0 plus the limit as t goes to infinity, x squared over 2 evaluated from 0 to t, right? But let's write that out, just a little bit more writing, and I'll get out of the way here. So you've got yourself a minus s squared over 2 limit and a t squared over 2 limit, right? And the thing is, these are both infinite. All right? One is minus infinity, the other is plus infinity. Now, if you're nonchalant about how infinity works, you might be like, oh, they cancel. But that is not how this works. These are not a connected infinity. This is minus infinity, this is plus infinity, but this does not exist, okay? It does not exist is what we say in this case. But the negative's outside the square. So it's not inside the square. Because it's the lower bound. So we do 0 squared over 2 minus s squared over 2. It's just that. So these do not cancel. To say these cancel is to suppose that you're taking the integral to be defined to be limiting in this symmetrical fashion, right? So all these improper integrals, they're defined in a limiting sense. So really what you're saying is you're calculating the area, you know, like under this, right? It goes from, say, minus t to t, right? You're calculating the area bounded by y equals x from minus t to t, yeah? And it's true, as long as you keep expanding that shape out symmetrically, it will stay 0. However, if you do one side one way and one side the other way, there's no guarantee that those are going to balance out, right? The notation plus infinity and minus infinity for the separate integrals doesn't maybe do justice to this idea, but it is the case that they're separately diverging and therefore they don't cancel. In contrast, here we have explicitly linked, incorrectly, mind you. This is incorrect, all right? This has a different name. What this is called, I can fix, you don't have to erase it. To fix this, what you do here is you put PV. PV. So this is called the principal value. It's the principal value of the integral. You can have an integral which diverges and yet has a existing principal value. These are important in applications as well as math. So, and they naturally arise in like complex analysis as well. Yep.
If we can tell it's an odd function and it has infinite bounds, can we just say that does not exist?
Yeah, I think as a generic theorem, if, I mean, I want you to work the integral out, right? But you can expect it not to exist if you're integrating something which blows up, right? If the limit of the function you're integrating is not going to 0, come on, it's not going to integrate. It's not going to have a finite area, right? Like these ones worked, right? This one and also this one, they worked out to be finite. My example 1 and 2, why? In part because the limit of the function was 0 in the integration region, right? In contrast, if you think about the graph of y equals x, it's bad in both directions, right? It's going to infinity this way, and it's going to minus infinity that way. So it's doubly divergent. So the next question that you would logically ask is, so are you saying that if the limit of the function is 0, that the integral will converge to some definite number? Like, is that sufficient? By now, you know, if a math professor is asking this kind of question, the answer is no, and it's something diabolical, right? Indeed, that's true. This is something that will plague a third of you for a third of this course. Let my prophecy be false. Please, let my prophecy be false. Not so much on this test, but like the second test, this is the issue. So let's look at an example where, in fact, the function goes to 0, and yet the area bounded by the function is not finite. So the best example I know of this is simply this. So this would be example 4, I think. Check this out. Integral from 1 to infinity of dx over x. All right? So this is equal to the limit as t goes to infinity of the integral from 1 to t. And so you guys are mostly engineers, I think. Am I writing limit just to see myself write limit? Or am I writing limit to try to impress upon you that you also need to write limit? Let this question remain unanswered. But hopefully the answer to you is obvious. Listen, so like, I mean, there is engineering notation, but you can use engineering notation when you get to engineering classes. And here, I need you to write the limit. So this is natural log of t minus the natural log of 1. Now, why can I drop the absolute value? What's the context here? We're taking the limit as t goes to infinity. Right? Certainly t is positive in that limit, so the natural log of the absolute value of t is just natural log of t, okay? Now, natural log of 1, we all know what that is without picking up a calculator, right? What is it? 0, right? I mean, you do have a calculator, so you can pick it up, but what's the limit as t goes to infinity of natural log of t? What's the graph of natural log of t look like? Do you know? I saw somebody who went like this. That's good. So, right, if this is the exponential, right, then the natural log is just a reflection of that dude across the line y equals x. The y-intercept of 0, 1 becomes the x-intercept of 1, 0. So there you go. Y equals natural log of t. All right. So a couple critical limits for natural log is it limits to minus infinity as you approach 0 from the right. Yeah. And it limits to infinity as t goes to infinity. It doesn't get there very fast, but it gets there. All right. And so what that means is that this, oops, it goes to infinity. So here, my friends, the answer is infinity. What that means is that if we look at the graph, of y equals 1 over x, which looks like what? Y equals 1 over x looks like this. It's a hyperbola. Right? It's a hyperbola that's tilted 45 degrees. If we had linear algebra, we could derive this using eigenvectors. But we don't, so we won't. But this is the graph of y equals 1 over x. It's a hyperbola rotated 45 degrees, like I said. And we just showed that the area bounded by that, despite the fact that at the limit of my artistry, it looks kind of about the same as the one I just erased. This area is unbounded. What does that mean technically? What's the precise meaning for that? That means that if you wanted to pick a subset of that area, which had area 3 billion, you could go sufficiently far out to have an area of 3 billion under that curve. Pick any number you like. You can find far enough out to find that area. That's what it means for the area to be infinity. In contrast, pi. No matter how far you go out, you can't get past pi area bounded by the bell curve here. This is not the bell curve, by the way. It's just a curve that looks like a bell. The bell curve is the Gaussian curve, right? And we should talk about that. But maybe not today. Any questions?
Do we have to draw graphs?
Yes, probably, in order to understand things. Yeah.
What makes that unbounded? Like it has a infinite area. Like what makes it to infinity if that one?
Basically because it doesn't shrink fast enough.
Oh.
And it turns out that this is kind of right on the bubble. If we do x to any power bigger than 1 in the denominator, like if I do x to the 1.00001, right? Then this would work out to, it wouldn't have a natural log, it would have like, the power rule, and you'd end up with something to the like 0.0001 power in the denominator, which would limit to 0 actually. This is right on the dividing line. So I shouldn't even show you this to you guys, but I will admit in engineering, after this, you will write things like natural log of infinity minus natural log of 1, and you'll be like, well, that's infinity. All right? But will that be written in this class? It will not. So this is forbidden in here for now. Once you pass this class and go on, you have my blessing. You use that notation in engineering classes all day long, fine with me. You might even catch me using it in a higher class. But anyway, yeah.
So I'm still confused how the unbounded one, how the area of that is, I think it was a pi or 1. And, how is that one pi if it like never gets to 0?
Right here. This is the meaning. Yeah, I mean, it never actually gets to pi, but if you pick me a number like pi minus 0.01, okay? I can go far enough out to get that area. I can truncate it. I can,
But it never gets to pi.
No, unless you go all the way to infinity and minus infinity. Asymptotically, it gets to pi. Now, so we haven't yet hit, yeah, oh. Let's see here. So another example, oh yes. Let me start to show you some of the danger of the engineering notation. Let me show you an example where it matters. Like I admit, this is a nice, quick, reasonable notation for sufficiently simple problems, but it will lead you astray for problems that are more subtle. All right. So an example of one of those might be this. Example 5. What if we were integrating, I don't know, from, let's say, 0 to infinity. Sorry. X e to the, I don't know, minus x dx. I'll keep it relatively simple in here. By definition, this would mean the limit as t goes to infinity of the integral from 0 to t of x e to the minus x dx, yeah? Now, in this kind of problem, I think it's in our best interest to go and do the integral, the indefinite integral, separately. So let's do that. Let's do this indefinite integral separately. All right? How do we do it? I mean, this might well be problem 1 on your test, yeah? What I'm writing here might be problem 1, who knows? Wouldn't be unreasonable.
Integration by parts.
Integration by parts, I like it. So we're going to make this our dv, make this our u. That gives us minus x e to the minus x plus the integral of e to the minus x dx. Because our u is x, our du is dx, our dv is e to the minus x, which makes v minus e to the minus x. Minus and minus gives me a plus in the formula for integration by parts, and that's what you got. So the answer is minus x e to the minus x minus e to the minus x plus a constant. I'm integrating by parts at a speed slightly faster than I was to start with, right? Okay. If you didn't follow me, that's because you're not yet up to speed on integration by parts, right? And that's okay. But you need to work on it a little bit. Maybe, my point is, if you have 3 minutes, you should be able to calmly and confidently get to this answer, assuming I haven't made a mistake, which would be hilarious right now, given that the posture I'm taking. Yeah, but I think that's right. We can differentiate it, yeah? If I differentiate this, the product rule gives me what? It gives me the derivative of x, which is 1, so I get minus e to the minus x, right? Then the other part of the product rule gives me a plus x e to the minus x, right? Then I differentiate that, and I get a plus e to the minus x. So the plus and the minus e to the minus x cancel, and I'm left with the x e to the minus x. So it works. All right? Yeah.
Is the derivative of x not x dx? Or is it just dx?
I had to do product rule. So when I differentiate x, when I differentiate the minus x e to the minus x, I get, minus e to the minus x plus x e to the minus x. The plus comes because minus and minus is a plus. That minus is coming because there's a chain rule for e to the minus x. But anyway, that's correct. So FTC2, what do we have? We have the limit as t goes to infinity of what? The integral, yeah, of minus t e to the minus t. Oh, my bad. I was trying to write down the answer. Minus t e to the minus t minus e to the minus t, all right? The constant doesn't matter, it evaluates to 0. What happens when I plug in 0 into this? The first piece gives me 0, the second piece gives me 1, so I get plus 1, all right? So all I'm doing is I'm calling this thing here I'm calling this thing here basically big F of x, yeah? And I'm observing that f of 0 is equal to minus 1, okay? That's where this plus 1 comes from. And then this is f of t, all right? And we can make c equal to 0. It doesn't matter, yeah? It cancels. How do you calculate that limit? I mean, I'll do the easy part. As we talked about just a minute ago, this guy, it goes to 0. What about the limit as t goes to infinity of, I'll drop the minus because it's kind of irrelevant, t e to the minus t. What kind of limit are we looking at here? L'Hopital's rule. So that's the question. Have you seen L'Hopital's rule before? You should have. You may or may not be current on it, but the reason we need L'Hopital's rule here is this is type what? This is type infinity times 0, right? So that makes L'Hopital's rule a good option here. So what we're going to do is rewrite this as the limit as t goes to infinity of t over e to the t. That's just algebra, right? And now, since we have type infinity over infinity, that is one of the two cases that L'Hopital's rule applies to. Right? Type infinity over infinity. And as such, we can apply L'Hopital's rule. I write, and this is my notation, I just write this fancy looking L with an infinity over infinity that says, hey, I'm using L'Hopital's rule. How do you do L'Hopital's rule? You differentiate the top, differentiate the bottom separately. Not a quotient rule, but separately differentiate the denominator and the numerator, like so. Yep. And now we've gone from type infinity over infinity to finite over infinity, which is not ambiguous. This just does what? This just goes to 0, right? So this is equal to 0. So by this calculation down here, we have now shown that this also goes to 0. All right? By all of this. Now, in the heat of battle, if you want to remember that, exponentials beat polynomials, I'm okay with that. But you should also be able to explain to me why that's true. That's what we've just shown. We've shown that exponential growth beats polynomial growth. And that's true even if you replace that t with like t to the 30th power. Because you can still just apply L'Hopital's rule like 30 times and get the same result. So if you're you've got a polynomial up against an exponential wins in these infinite limits, in this sense. So what's the answer? The answer is 1, yeah. Oh man, it seems like so many of the answers work out to 1, but oh well, it is what it is. Any questions? Yes, sir.
So would you expect to see how you pronounce that rule?
L'Hopital's?
Yes.
Yes, I would expect to see L'Hopital's rule where it's needed.
What if we just like plug big numbers in the calculator and solve the proof from 0?
Well, that wouldn't be a proof. Part of your job in here is to explain why things are true. Now, would that get you significant partial credit? Probably. It would be like way, way better than saying, it goes to infinity or something. Because that's sometimes, I just don't know what students are going to do. When they get infinity times 0, sometimes they pick 0 as the winner, sometimes they pick infinity as the winner. You could go in sometimes this works out to 2. That could be the actual answer.
Was it one of the...
It's indeterminate. It could work out to anything is the point.
Was it one of the types for law? I don't know how to pronounce that. I never learned.
L'Hopital's?
It wasn't.
Just call it the hospital
minus
rule.
infinity?
It's fine. What?
Was it one of the types of infinity minus infinity? And you had to like work it out?
Oh, yeah, another one.
Because, that was one of the problems that we had, infinity minus infinity.
Here, we'll look at another one here. How about this? Integral, say from 0 to 1 of I don't know if I can do that. Rats. Oh. This may be kind of sketchy. Eh? So what this should mean is the limit. This is you've driven me to this. This is your fault. This may or may not make sense, but the rest of you can forgive me for this. But what's the antiderivative of the derivative of sine x over x? Sine x over x. That was my point. I wanted that. So limit as a goes to 0 from the right of sine of 1 over 1 minus sine of a over a. All right, that's what I was after. I just wanted us to look at the limit of sine a over a. All right. I could have maybe I should have just said that separately, right? That would have been like less weird. My point to you is this sine of 1 over 1 is whatever it is. It's a number, yeah. So we got like sine of 1 minus the limit as a goes to 0 from the right of sine a over a. Now that's the other case where L'Hopital's rule is relevant. Let me write it. Somewhere up high. You guys okay if I erase this gift of a test 1 problem that's up in the corner of the board? Yes. When's test 1? Next Thursday, I believe. Yeah. Let's see here. So if we want to calculate the limit as a goes to 0 from the right of sine a over a, well, first of all, some of you may just remember from basic principles what that limit is. What is it? 1, right. We can prove that with a squeeze geometric theorem looking at the unit circle and appropriate triangle and stuff. But forget about that for a second. Suppose you forgot it. This is type what? It's type 0 over 0, right? It's because sine of 0 is 0, and a goes to 0 as a goes to 0 from the right, right? So we can apply L'Hopital's rule. So L'Hopital's rule, this is type 0 over 0. And by the way, the only place that this symbol appears is on the board for me. It's above my current LaTeX skill. Like I haven't figured out how to do this in LaTeX yet. Otherwise, it'd be in my notes. This was shown to me by my Calculus 2 professor, Dr. Ernie Lane of Appalachian State University. Worked for NASA before it was NASA, yeah.
On the test, should we write that funky symbol?
You can write, yeah, you can write the funky symbol, or you can write off to the side. I'm using L'Hopital's rule, or just like lo. You could do it like this: la hop, la hop, la hop. You know, and then either infinity over infinity or 0 over 0. Just tell me that you have thought through applying it correctly.
Do you want us to specify like the type?
Yes. Yeah.
Can you put an L over the equal sign? Like a capital L?
You don't like it going through the equal sign. You want it to go over the equal sign. Yeah, we could probably do that. But that's not how I was taught, so
You
I know.
write like a smelly Frenchman?
Right, what?
Smelly Frenchman?
Smelly Frenchman. Isn't that redundant? But, oh, I'm sorry. Are you guys French? I was telling my college algebra class the other day that I'm probably part French, but I'm pretty sure it's the part of me that I loathe. But I'm sorry, we don't have a lot of French here. It's safe to pick on them. They're lovely people. They've got an Eiffel Tower. We don't have one of those. What do we got?
We do.
We have in Las Vegas. I don't know. I think you don't want to. If you take a look at the Middle East, you don't want to be bragging about towers these days. But I was talking about the incredible towers in Dubai. To be clear, if that was somehow interpreted as another kind of joke, good for you. That was purely accidental. The best jokes are accidental. Let's see here. Anyway, we're well on our way to editing this video, aren't we? Rats. No, I'm leaving it. I'm leaving it. All right, so so begins the story of how Dr. Cook got fired in the year 2023. Okay, anyway, hopefully not. So differentiate sine, we can all do that. Cosine of a. Derivative of a with respect to a, 1. What's the limit then? Cosine of 0, which is 1. So setting aside the issue of how exactly are you differentiating this function at 0 exactly, right? This function's not even defined. Actually, this is actually not a bad example. So this is the issue. It's kind of manifest and it's in your face here. This function is not defined at 0, right? Yet we're doing what? Integrating from 0. What do you have to mean when you write something like that? You have to mean it in a limiting sense. All right, that's the other kind of improper integration. So anyway, long story short, the answer was sine of 1 minus 0, sine of 1 minus 1. And I'm sorry, I seem to have gone over time, so I will shut up. Yeah. Sorry. I blame the joke.